Assalamualaikum and good afternoon everyone. We are from Group A1Y. Today we will be presenting about our last experiment regarding residence time distribution in tubular reactor. My name is Amira, ID number 18624. I will explain to you the introduction, abstract and theory of residence time distribution. Based on our experiment, my colleagues Ami and Rajan will explain about the calculation and the result and calculation from the experiment, followed by Wenxin who will explain to you about the discussion. Later on, Fahmi will wrap up our presentation in conclusion. First of all, the objective of the experiment is to determine the effect of liquid and gas feed rates on the mean residence time and the degree, which is the intensity of the liquid phase axial dispersion. We do the experiment in order to understand more about the application of residence time distribution in chemical reactor, since chemical reactor is very essential in industry. Residence time distribution is actually a characteristic of mixing that occur in the chemical reactor. In other words, residence time distribution, or in short RTD, can be known as the time spent by the flowing fluid in the chemical reactor. Moving on to the theory. In order to measure residence time distribution in chemical reactor, an inert chemical named tracer is injected to the reactor at T equal to 0, and the tracer concentration is measured as a function of time. The tracer must have the same physical characteristic as the flowing fluid in the chemical reactor, and the tracer must soluble in fluid yet cannot be absorbed by the wall of the reactor. The most commonly used tracer are radioactive and colored material. There are two methods of injection of the tracer to the reactor. First is pulse input and second is step input. The function of residence time distribution can be extracted by the tracer response curve of concentration versus time as shown in the figure. Later, I will pass the floor to Ani, who will explain about the calculation and result from the experiment. Thank you.
Hi everyone, my name is Yi and my ID number is 16150. And now I'll present on the results and calculations for our experiment. To make things easier, I'd like to use the results from part A, which is to study the effect of step input change. First, we tabulate this data, and we are given the liquid flow rate, which is 0.5 liter per minute, and also the air flow rate, which is 3.9 liter per minute. And then we tabulate this data. The time and conductivity is given, is what we obtained during the experiment, and then we need to calculate the residence time, concentration of tracer, time minus residence time minus residence time squared times residence time distribution, as well as time minus time residence time cubed multiplied by residence time distribution, which will be used for the later calculations. So we'll start by calculating the integral of the concentration, tracer concentration. By taking the integral, we are using Simpson's rule, and we can calculate the area under the graph. And for this experiment, what we got is 22.6175 units squared. And step 2, we'd like to calculate the residence time distribution, which we take the concentration divided by the area that we obtained just now, which is approximately minus 1.54 times 10 to the power negative 3 per minute. And next, we'd like to calculate the mean residence time by taking Simpson's rule as well, which we are taking the integral of time multiplied by residence time distribution. And for this experiment, what we got is 18.01 minutes. And next, we'd like to calculate the variance by taking Simpson's rule. Now we'll take time minus residence time, and we'll multiply with the residence time distribution. And what we got for this experiment is 17.05 minutes squared. Next, we calculate the skewness. To calculate skewness, we'll take the integral of T minus Tm cubed multiplied by residence time distribution. And for this experiment, what we got for skewness is negative 1.2606. Last but not least, we'll determine whether the system has negligible dispersion or large dispersion. So now, we'll calculate the dispersion value by taking variance over tau squared. And what we got for this experiment is actually 0.026. And then we can conclude that since the dispersion is larger than 0.01, the system has a large dispersion. And now, I'd like to pass the floor to my colleague, Yuvarajan, to continue on the tabulation of the results.
Thank you, Yi. My name is Yuvarajan Mohan and my ID is 16179. So I would like to continue further on the effect of step change input for counter current mode. So this is the graph that we obtained from our results, which is a graph of residence time distribution against time. So based on a graph, we can divide this into few phases. The first phase is the lag phase, and then an exponential increase phase, and then another lag phase, and here is the constant phase. So based on this, we can conclude that our graph follows the theory of method of injection for step input. So next, I would like to go to the co-current mode, and here's the calculations, the results that we obtained. The calculation method have already been mentioned by my teammate just now. The mean residence time, we got 20.90 minutes. For variance, we obtained 9.3295 minutes square. Skewness, we had 38.309. And here, our dispersion was 0.0108. Since our dispersion is still more than 0.01, the system has a larger dispersion. So now, for the graph for co-current mode, it's again the same graph for time distribution against time. And here, we have a much more nicer graph, and again, this is the lag phase, then this is the exponential increase phase, and here's another lag phase, and here is the constant phase. So more on the graph will be discussed later. Okay, now for the part B, to study the effect of pulse input. So here are the results and calculations we obtained for the part B. First, for the counter current mode, the mean residence time is 19.59 minutes, the variance is 111.61 minutes square, the skewness is 43.48, and for the dispersion, we have obtained 0.145. Still, it's more than 0.01, so the system has a large dispersion. So now, let's look at the graph for counter current mode. So this graph is again based on time distribution time against time. So here, we're supposed to have a smooth curve for pulse input, but due to some experimental errors, we obtained a graph that is a bit, a not accurate one. But still, we can conclude and compare with the theory. So here will be a decay, and then an exponential increase, and then a decay, a lag, and then it's constant, and it becomes decay again, and then it exponentially decrease, and then there's another lag. So here, for the part B, effect of pulse input, co-current mode. The mean residence time is 20.43 minutes, the variance is 158.875 minutes square, the skewness is equals to 56.27, and here the dispersion here is 0.1903. So since the dispersion is still larger than 0.01, it has a larger dispersion. Now for the graph for co-current mode, here the graph of residence time distribution against time, we have not a very smooth curve for a pulse input, but then here again to explain, and there's a lag phase, exponential increase, and then here's a decay and a constant phase, and another lag, exponential decrease, and then a lag. So here, based on the both graphs, I can conclude that our counter current mode has a more efficient residence time distribution, but it has its disadvantage, which counter current mode has a higher residence time distribution.
Hi, my name is Suman Singh, and today I'll be talking about the discussion of this experiment. This experiment is separated into two parts, Part A and Part B, where in Part A, we are changing the step change input to study the effect of air and liquid feed rates against the residence time in the tubular reactor. This experiment is carried out in two types of operational mode, namely counter current and co-current flow. As we can see, in the counter current experiment, the lowest value of residence time obtained is negative 0.00164 per minute, and the highest value is 0.0868 per minute. On the other hand, in the co-current experiment, the lowest value of residence time is negative 0.01359 per minute, and the highest value is 0.0814 per minute. Now, in the mean residence time, we can see that the mean residence time of the counter current flow is shorter than the mean residence time in the core current. In counter current, we obtain a mean residence time of 18.01 minutes, while in the core current, we obtain a time of 20.90 minutes. Skewness is actually a measure of the degree of asymmetry of a distribution. We can see that in a counter current experiment, the skewness obtained is negative 1.2606, and in the core current, it is 38.309. It is shown that the skewness is higher in core current mode compared to the counter current mode. Now, conductivity is based on residence time. The lower the residence time, the higher the conductivity obtained. We can see that actually counter current flow has a higher conductivity compared to core current. This is because in counter current flow, the salt solution moves at a faster rate from the top of the reactor to the bottom. It is also helped by gravitational pull and as well as the heavier density of the salt solution. So now I'll be talking about part B of our experiment, which is to study the effect of pulse input. The objective of this experiment is to study when we change the pulse input, what will happen to the air and liquid flow rate against the reactor time in the tubular reactor. Once again, this experiment is carried out in two types of operation mode, which is counter current and core current flow. The residence time in counter current flow, the highest value we obtain is 0.0807 per minute, while the lowest value is 0.0112 per minute. In the core current flow, the highest value of residence time obtained is 0.0733 per minute, and the lowest time is negative 0.0588 per minute. In the mean residence time, we can see that once again the mean residence time in counter current flow is shorter than that in the core current flow. The mean residence time of counter current flow obtained is 19.59 minutes, while in the core current flow, the mean residence time obtained is 20.43 minutes. This time, skewness obtained in counter current flow experiment is 0.23837, and in the core current flow, the skewness is 0.21829. So now that we have already talked about experiment part A and part B, we will now do some comparison. We can see that step change input has a higher mean residence time compared to that of pulse change input. This is because in step change input, the flow is flowing continuously into the reactor, resulting in a higher density and a higher mean residence time. But in the pulse change input, there is only a pulse inject of the flow. And in conductivity, we can also see that step change input has a higher conductivity than that of pulse change input. This is explained that because when the pulse of salt solution is introduced into the reactor, the ion concentration available is lower to conduct electricity, thus the overall conductivity is low. In conclusion, this makes counter current more effective than core current flow. Since I've already finished talking about the discussion of our experiment, I'll now like to talk about the errors and recommendations. The graphs we obtain is slightly different from the ideal graphs given. This might be due to some errors we committed when carrying out the experiment. One of the errors might be systematic error, where there is some error in the calibration of the instruments. This can also be known as zero error. Then there is also random error, where when we are taking the reading, the height of our eyes is not directly perpendicular to the reading of the instrument. This is also known as parallax error. Besides that, there might be some bubble trapped inside the reactor, left over by the people who did this experiment before. There might also be some spillage when pouring the solution into the tank. The recommendations suggested are as below. First, we should make sure that the position of our eyes is perpendicular to the skew of the beaker when taking the reading. Next, we should ensure that the trapped bubbles are removed first before we start our experiment. And finally, we should make sure that there is no water spillage when we are pouring the water into the tank. And now, I've already finished my part. I would like to pass the floor to Fahmi, who will conclude our presentation.
Bismillahirrahmanirrahim. Assalamualaikum. My name is Abdullah Fahmi bin Ize, ID 16240. And today I will present about conclusion. Okay, basically this is our conclusion for experiment. Okay, so for experiment A, the first point that we got is the residence time for counter current flow is higher than co-current flow. This is caused by the high resistance of sodium chloride particle to flow inside the reactor column. Okay, actually this phenomena is being shown by the flow of gas and water feed from the bottom part. Okay, for our second point, the resistance for the tracer to flow in the reactor column is lower for co-current flow. Why is this happen? Basically, this is caused by the particle of sodium chloride is carried out from the column by air and water, by gas and water. This causes a shorter time for the particle to stay inside the column. And for our last point, both co-current and counter-current process reach its maximum concentration equilibrium after some times. And for experiment B, our first point that we get is the residence time for counter-current flow is higher than co-current flow. And why this happen? This actually support the theory that actually we need a longer time is needed for sodium chloride to stay in reactor column in counter-current flow compared to the co-current flow. And for our second point, there's a tendency of dead zone forming in the reactor column for the co-current process. And why this happen? Actually, sodium particle tend to flow in lower concentration, lower resistance paths inside the reactor column. And this actually cause ununiform particle distribution inside the reactor that cause dead zone forming. And for the last point, the concentration for this pulse input experiment for both co-current and counter-current will come back to its initial concentrations as all the particles exit the reactor column. As a roundup for our video today, basically we achieve our experimental objective, which is to prove that residence time is actually higher when you enter the feed through counter current flow compared to the co-current flow. Okay, that's all from me and my group. Thank you to Madam Taslima, and we hope you enjoy this video. Assalamualaikum and goodbye.